So today is lecture 9 on invariant maximality reversal, part 7 by Harvey Friedman. Please.
Thank you, Andreas. This today is on the fourth section of the reversal. So 4.4 means chapter 4, section 4. Chapter 4 in this book and section 4. And uh, the text of the previous lecture, which was on section 4.5 of the reversal, is already on my both on the downloadable lecture notes page, the actual lecture, and there's also the polished version of the actual reversal in detail on the downloadable manuscripts page. So let's review where we are. As I always say, we're actually reversing this statement. Every order invariant graph on q minus 1, 1 to the k has a invariant maximal clique. By the way, I have vacillated between using a comma here or a semicolon, and now I've decided it's going to be a semicolon because this actually is meant to refer to a function. This is not a list. This here is not a list, really, as much as it is this whole expression here without the slash is actually the name of a function, right? So every order invariant graph has a blah invariant maximal clique. Okay, as usual, no change for forever. And reminding you that if we don't have this, if we're just going to do invariant with respect to this function, then of course it's provable. All right, now we have, of course, we always review that this reversal is in 11 sections, and we did 11, 10, 9, 8, 7, 5. 6 is a bookkeeping chapter. It'll be clearer what I mean by bookkeeping chapter when we talk further into 1 and 2. But it's an important thing because the definition of the order invariant graph is a monstrous thing, and it gets kind of rolled out in the reversal. It kind of gets rolled out in sections 1 through 5 from time to time. So you have to actually justify that you've done this legally. You've really actually legally defined a graph. All right, so we're doing negative reduction. The reversal really starts in 3. So we only have one more lecture of real meat. But we still have to have another lecture on these two. I'll probably combine the lecture. I may do 4.1 and 4.2 all at once. I may not split it. But next lecture is this one. And the 4.1 and 4.2 are infrastructure lectures. This is all infrastructure so we can get the thing going. All right. So down here, at the risk of repeating some of the things I just said, we're going to discuss 4.4. Now, to add context, we got to talk about what leads up to section 4.4. After preliminary sections of 4.1, 4.2, the reversal starts in earnest with section 4.3, as I said. And in 4.3, we just choose a number k, which is kept fixed throughout this reversal up to a certain point that we've already talked about before. Because remember, we're doing the backwards thing. You remember at some point we don't have k. We universally quantify over k because we said that we never used anything about k except that it was big. 1,000/1 is 2 to the 1,000. So we apply the statement being reversed to a complicated order invariant graph G on q minus 1 k to the 12. K12 is 12 twos with a k on top. 12 twos, exponential twos with a K on top, taking an arbitrary maximal clique of the graph, and that is invariant. Okay. In section 4.3, in other words, the section preceding up to the one we're going to talk about today, which is 4.4, we make heavy use of the invariance of S applied in several ways to this system. You can think of this as a system. The domain of the vertex set of the graph. Well, no, Q minus 1, 1. The base set of the vertex set of the graph, and these particular numbers with less than, and S is the invariant maximal. S is the invariant maximal clique. S. So these numbers act as indiscernibles, and S is a K12 Airy relation, of course, because it's a subset of the vertex set. And the vertex set is Q minus 1, 1 to the K12. K12 being 12 exponential twos with a K on top. All right. Now, in section 4.3, we develop both atomic representations for the set suitably defined and indiscernibility of these numbers. Indiscernibility, so to speak. These representations and indiscernibility use certain finite languages, and we've discussed these languages before, but let's review them. These are the three languages that we use in section 3 for the representations and for the indiscernibilities. We apply this to pieces of the maximal clique, as we discussed below, the K airy piece, the K4 airy piece, and the K8 airy piece. All right, so this language has K1 variables, and its complexity of the formulas is K1, and their quantifiers and connectives, and the relation is K airy. Here, the complexity of the formulas is K5, the number of variables is K5, and the arity of the relation is K4. And here K9, K9, K8. But the zero means that we only care about the quantifier-free part. So it's only the quantifier-free part that we care about with these other two languages. This language, we have quantifiers. These are auxiliary languages. We bring them in because we have to approve a lot. We want to prove a bunch. We want to prove what we want about the main language. These. Okay. All right. So these finite languages are, well, I'm repeating myself. Same thing. Okay. And how do you take pieces of a K12 airy relation S? The pieces are defined S/T is the set of all T tuples, so that when you extend it to become a K12 tuple, by repeating the last term forever to fill it out to be of the right length, it's a member of S. Okay. Now, there are no constants in these languages. All right. So here is what section 4.3 ends with. It ends with 3 representation theorems. Actually, section 4.3 doesn't discuss indiscernibility at all. You know, there's indiscernibility of the very basic kind that comes from the statement, comes from the fact that S is that the clique is invariant with respect to that function, right? That function. What function? In the statement, the function is this function here. Okay. All right. So the first of the 3 theorems is the representation theorem for this language. And basically, it says that if you have a formula in this language, phi I, so this indexes the formulas. T of k is the number of formulas in this language, which is finite. So if I have a formula in this language and I have parameters below q, k1 parameters, in fact, where q is negative, then we have you have an atomic, a negated atomic and atomic representation for satisfiability. In other words, what are the assignments that make this true? What are the assignments X that so that SK, phi I, and X hold with the quantifiers ranging over all the quantifiers ranging over less than Q. That's what that SAT means. Okay. And it's actually just not S, but with these parameters that go all the way up to 2I, and then they repeat. And it's also the same as without the negation sign, just S with one more of these things. So we're representing satisfiability in this language up here. We're representing satisfiability quantifying over quantifiers range over less than Q, where Q is in here. We're quantifying it. This statement is equivalent to a very simple statement, negated atomic or atomic, involving X, Q, and these parameters. So we're using these indiscernibles as parameters. This is an important idea. And here it's one more with the S. And we set this up. This is set up because of the way that we built the graph. The graph is designed so that this is the case. See, we have to show that we can do that, right? So we designed the graph so that this becomes something that can be proved manageably by induction on the formula phi. All right. See, the index of the formula I appears in how long this is. See, and the Q appears here, and the X appears here. Now, this is the most embryonic baby form of comprehension. Eventually in this reversal, we're going to get a representation of a more powerful SAT, also in a simple way like this. We're going to get that, but we're going to have it with only 5 parameters. See, this is because we've gone backwards in the lecture series. You remember this business about five parameters. You remember this kind of thing we did. Yeah. Okay. So now this is the one that this is the most serious one, but we also have to have a representation theorem for the quantifier free stuff. Now, what do I mean by representation for the quantifier free stuff? I mean the same kind of thing here. We want to get rid of connectives and quantifiers. Here the thing I'm showing you right now, we got rid of both connectives and quantifiers. See, in regular quantifier elimination and O minimality, you just eliminate quantifiers, you don't eliminate connectives. But in abstract set theory, you also get rid of connectives, right? Because you're representing by membership in a set, and you have one parameter namely the set. Where here, we represent also without using any we also get rid of the connectives, just like the set theory, except it's more complicated situation in terms of what we're in terms of the representation. The representation is an atomic formula or negated one with a lot of parameters. Okay. All right. So for the other 2 languages, it's convenient to look at 2 special sets. The negative numbers plus the indiscernibles. Actually, you don't want the last one. I mean, for technical reasons, Be- because you can't shift the last one. And then you take the K tuples, the K5 tuples from there, and the K9 tuples from there. You also don't want them to go all the way up to the top for technical reasons. So we say that the max is not just less than or equal to one, which is free, but less than or equal to a half, which is kind of arbitrary. But a half is a very big number in these. Is way out in this list of indiscernibles, right? It's halfway there, which is a long way. All right. So we also want to use this notion of double max, where you want it's just the max of zero and the max. Uh, we just want to make sure we get at least zero out of tuple. This is all technicalities to set it up. And so uh, the representation says that I can represent sat uh, uh, for this language um, if and only if uh, we go out uh, we go out 2b plus 1 in here. And y is very long. See, because y is a K5 tuple, you see. So we're really going out quite a bit higher than we ever were in the other language. You have to make sure that these statements don't collide with each other and create conflicts. So this is clear because y is very long compared to what we're doing over here. And so we can do that. Uh, and then the same thing for even the larger language. So that's really where section 3 starts, where we start from section 3 at the end of that's the end of section 3. All right, so now we're talking about the present section. So note that these numbers 0 through K12 over 12 K12. By the way, for technical reasons, we started with 1 over K12 over here, but you can shift to the left because we have that just from the statement. But anyways, all these numbers, 0 is still important. These act like very weak indiscernibles with the invariance. Yeah. J is the definition of the function in the statement we're reversing. I let J be the function. J is actually the function of this function here. I let this be J. J invariance. This J invariance is an extremely weak form of indiscernibles, right? And yeah. And what we do now, I should have, say this more clearly. What we do now, of course, well, I said it before, I'll say it again. In the original statement, we have K, but we set K to be K12. And we set K to be a particular finite number, a particular finite number that's large, that I said before, a large finite number K. And we use K12 instead of K here. In the statement is applied to K12, also with arity K12. We have a maximal clique of a graph. The graph is also in dimension K12, and the indiscernibles are of length K12 plus 1. I guess they go from 0 to K12 over K12. All right, so these indiscernibles are very weak. They're only finite in number, K12 plus 1, I guess, and we can't jump around since adjacency is required. So normally in indiscernibles, you can jump around. Only negative parameters are allowed, and only atomic formulas are preserved. There's no nesting, is there no function symbols involved. There's no constants or functions in the languages. So that's what we get just from the statement. And then the point of this, then we have these representation theorems here. So the point of this section is twofold. First, to get much stronger indiscernibles, in fact, infinitely many of them, negative numbers whose sup is 0, where we can jump around preserving statements in the language, our most important language, using parameters below the lowest indiscernible being used. This is a big improvement in the indiscernibility in the theorem 4412. To achieve this, we first prove an even stronger indiscernibility for the but this time for the quantifier free language, this quantifier free language, we show indiscernibility with respect to this quantifier free language for this system with all the R's, these negative indiscernibles, and the positive ones, the old positive ones retained without the zero. This is a technical thing. It's very convenient not to have it, but it doesn't make any difference. You could shift it. It's really the same. So this is an infinite sequence. It's an infinite sequence followed by a finite sequence, where we can jump around using parameters below the least indiscernible used, where still all parameters must be negative. So it's important that all parameters be negative in all of these things. There's a reason for that. And there's a lemma 4410 in which we state this strong indiscernibility. I mean, not that strong because the language is weak. And also, the indiscernibles don't involve, the indiscernibles have, there's parameters anywhere here, negatives, but there's no parameters that are positive. Positive parameters in this whole reversal are kind of impossible to work much with, because the original statement we're reversing only uses negative parameters. So positive parameters, even cleverly, can't be handled very well at all. That's why we have this section called negative reduction, because we want to push everything in the negative part where we can do much more. But we can still accommodate the positive indiscernibles and the negative parameters, but not these positive parameters, which we never use. These positive parameters are too dangerous. We don't have enough power in the statement being reversed to handle them and control them. Okay, second, using this indiscernibility, we convert the representation theorem 433 that we just talked about, that uses parameters here, to a corresponding representation theorem for this language using parameters R1, R2, dot, dot, dot. Yeah. I may have been a little bit ambiguous about careless about the use of the word parameters. They're the unruly parameters lower than the indiscernibles, and then there's the parameters added on in order for the representation. Added on for the representation that's higher than where the quantifiers are ranging over. All right, so this will become sort of clear as we get more specific. All right, in order to start this, we have to have a way to move 0 to a negative number. Well, actually, we have to have a way of moving. The way I set it up is we have to have a way of moving. Here, you can see what I'm talking about. We have to have a way of moving 1 divided by K12 shifted to a negative number. Well, I'm going backwards here. You have to have a way of taking 1 over K12 and replacing it by a negative number P and moving everything over without changing the truth value. We have to. How do I do that? Well, obviously, it's not plausible that I could use any old P. So I call P good if and only if it's non-negative. And you can use it to shift down, and you can use it for entry into the negative numbers. That's what P is good means. More specifically, it means for any formative phi, and if the numbers match up right, aren't too big or something, then SAT of XP 1K12 through J minus 1 is equivalent to pushing the P up to 1 over K12. I set it up so you're pushing up instead of pulling back. It might have been better to do it the other direction, say it the other way. But we all know that if and only if is commutative is symmetric, right? If and only if it's symmetric. So you could think of X being pushed to, excuse me, 1 over K12 being pushed to P, and the other one's coming down. Okay. So it turns out that being good is somewhat difficult to prove that it takes some work to prove that there are these good P. I mean, it's going to be fairly clear that 0 is good. I mean, it's not 100. I actually center it out as a little lemma or a theorem, but it's pretty clear that 0 is good, because all that would mean is I can shift 0 through j minus 1 of these all the way up to 1 through j, and that's exactly what's given by the original statement I'm reversing, except not quite in this context. But since psi is quantifier free, it's pretty clear that this is going to be true by induction, because you're just talking about propositional combinations. So this is sort of obviously true when p is 0. But the question is, I want to get negative p so that this is true. The pressing issue is to find negative good p. The general idea is that if 0 has a suitable property, then some negative number has that suitable property. Now, you have to make that rigorous and be careful, because we're in a very impoverished situation, right? So for the property of being good, this has to be argued carefully. The plan is to put p in order to do this, we have to put p is good into more and more manageable forms. And then we can do something magical to show that if 0 is good, then something negative is good, where arbitrarily large negatives are good. But we first have to get p is good in a very good form. There's 2 goods in there. P is good in a splendid form. Okay. All right. So the first thing is just to normalize things and make the length of things match k over k5. See, the length here is k5. This is a kind of a boring thing. That good is the same as looking at this situation. All right. It's the same thing. I'm pushing p up to 1 over k12, or I'm pushing 1 over k12 back down to p and shifting over. Okay. So now we want a version where we move away from sat and just use S, the k12 area relation, to characterize p as good. So we're gonna make p as good more manageable. So the next step is p is good if and only if we have this for the lower than p parameters, we have this equivalence, which is the same thing. I mean, we're just shifting back, but we're doing it in the context of S instead of sat. Now, this is actually clear just from the representation theorem for our second representation theorem for the language K5, K5, K4, because SAT is equivalent to S. So this is really just bookkeeping thing that comes from what we already have. Okay, so we've got it down into S, but we don't have it. I mean, I'd love to have this just with an S. We have it with if and only if. So this still has connectives in it. This characterization of good still has connectives in it. So we handle this by going to a third language, because this language quantifies overall formulas in this second language, K5, K5, K4, because those are indices. Those are just indices of the formulas, right? So this is very naturally put in. I mean, that's an enormous conjunction. So this is very naturally put as a single statement in this bigger language, K9, K9, K8, where we have more variables, although that's not as important. We have more variables and we have more we have more complexity, which is important, and we have more arity for R. Okay, so we can view the above equivalence as a statement in this language as the case 12 in here kicks in only a coordinate K5. And these numbers K5 and TK4 are much smaller than K8. This will allow us to use the third representation to put P is good in atomic form, right? In other words, using the representation theorem for this biggest language, this third one. And so here's some details, which you probably don't want to hear, but just to show you, did my homework. We break this yeah, this equivalence down. So it's RK8 of these things if and only if the statement is the statement is an if and only if. Remember, the statement is an if and only if. So we want to just formalize it. There we are. There we are. And but we're quantifying over a bunch of stuff which is not quantifiers. It's just a big conjunction, right? So these formulas we translated into the third language look like this thing if and only if this thing, right? And the connective if and only if, of course, is eliminated. I use only these two connectives. That, you know, officially only these two connectives. And this formula alpha bi, where B and I are used in here, this formula is rho of something, right? In other words, it's got index. The index is C of bi. So now the lemma 443 says P is good if and only if P is non-negative and for all the usual setup, X below P, sat. That's completely clear by the way I set up alpha bi, right? In other words, that if and only if is now replaced by a formula, right? But alpha bi still has connectives. And then we apply connective elimination. In other words, the third representation theorem from section 3. We apply the connective elimination. Now we don't have any quantifiers to eliminate, to get not S of a big mess from the, so it's this front stuff, which is this, together with together with these extra parameters that are indiscernibles, these indiscernible extra parameters. Okay. And that's immediate from the third representation theorem from section 3. And immediate from the definitions that were made of stuff here. Okay. So this is very good definition of P is good. We've now got it to a negated, ugly negated formula. But now we use the fact that the graph G was cleverly constructed, anticipating its need, and we put it in a nice form. P is good if and only if P is non-negative and S of all the way up to 1/8. Okay. You see, so we can do that. Yeah. See, this is going to be a set of formulas of this form, and you can actually make that into one. Yeah, so there's something to do. This is a set of negated formulas. This is not a single one, because it says for all B. So there's T of K of 4, that's a big number. T of K of 4, number of formulas in that language. That's how many of these things there are, and you want to put it into one. And that you can do by making sure that the graph behaves properly, that the graph is set up right. All right. So all right, now I get a little technical about zero is good. I mean, we kind of argued that zero is good is trivial, but now we can put more details on it, uh, so we J is the mapping in the statement we're reversing. So I claim that I mean, for atomic formulas, this is trivial from the original statement, but this is quantifier free formula, and so obviously this is preserved under connectives, under connective combinations. So this is sort of obvious. Okay. So zero is obviously good uh, because S of zero, uh, S of these things at K12 is true. Yeah. I'm trying to remember that maybe that's from maybe that is also something trying to remember how this is set up. Yeah, that's something also done in section 3, I believe. Yeah, that S holds of these when you have nothing to the left here. That S holds. Yeah. Well, no, I'm sorry. Zero. I'm not saying this right. Uh. Yeah. Zero is good. Yeah. Okay. We know that zero is good, and then this is just repeating that zero is good. Yeah. All right. Maybe I should. Let's see. How do I clarify this a little bit? All right. Let's not worry about this. This is a triviality that I haven't set up right. Set up completely right. Um, let's see. All right. Let me continue here. So now we want to prove the existence of negative good P. Um, and uh, oh, I see. Yeah, I use this and go back to the original definition of good and use this. I'll go back to one of the equivalences of good, and it's trivial. Yeah, so this is not an issue. All right, so um, we want to prove that there are arbitrarily large negative good P, and the idea is clear. Since zero is undefinable, like a critical point in an elementary embedding in set theory, if S holds like this, then it should be able to replace zero by arbitrarily large negative numbers. But we have to argue carefully in this impoverished situation that we can just reduce zero. So, so I I have a way of doing that. Uh, Let me say a little bit about how this works. See, this ends in this. This is what we want, right? That there is a good P that's bigger than Q and smaller than zero. All right, so uh, this is clear because you can set P to be zero. And then I use the construction of the graph to put that in negated atomic form. And then I shift to the left by J. In other words, this is just the indiscernibility, the invariance that the original statement gives me. And then uh, I get this statement from the same way that I got this. from the graph. And then I shift back up here, shift these up again. And then that's what this means. P is good. That's the definition of good. Okay. So we get arbitrarily large good, P less than 0, i.e. for all formulas psi, so I'm just repeating the definition. For all formulas psi, we have the original definition of good. All I'm doing is repeating that, right? So P and 1 over K12 get exchanged and be pushed down. So now we can, because we have arbitrarily large good, negative good, we fix them, R1, R2, R3, dot, 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 be an infinite sequence of negative goods with sup 0, converging to 0. Okay. The next step is to show that what we want to do is show that these things, in other words, all the R's together with the old indiscernibles, it doesn't make a difference if I put 0 in here or don't. So I think it's uniform. To keep it uniform, just keep 0 out. So if I have these negatives and I have these indiscernibles from the original statement, that this forms an infinite sequence of indiscernibles with jumping around instead of just always consecutive, with jumping around with negative parameters below the first indiscernible being used, and these indiscernibles for this. And that's done in a theorem 4410, which we're about to approach. So I want to say something about how that's done. Okay, so I let W be this. I'm a little worried. I think I used W for something else. Yeah, I've used W for something else. I think I'm gonna have to change this letter. All right, let's not do that. Change the letter right now, because then I have to pick the right letter. All right, but anyways, we have this set. We have all the negative indiscernibles and these old positive ones, these new good ones, and we say that Y and Z are star equivalent. Uh, uh, I think I meant to put an exponent in here, didn't I? Oh, here. Well, yeah, Y, okay, no. That's fine. Y and Z are star equivalent if and only if the following holds. Let psi be a formula and Y and Z be strictly increasing sequences from this set here, from this set of the same length. And let X be a non-empty sequence from W of that length, and the max is less than 0 and the min of YZ, then we have equivalence. So this is really the kind of indiscernibility we're looking for. I'm just giving a name for it. See, this is what we want. This is we want to have always star equivalence, but we have to define it first. So it means that Y and Z behave the same with respect to parameters low down. That's what this means. And Y and Z are from this nice set here. Okay. All right. So that's what we want. And then we show that if I don't use any of the positive ones upstairs, if I just use these, just the R's, the negatives, and they're both of the same length and strictly increasing, that's what n less than means, then the Y and Z are star equivalent. That's obviously what we want, and that's actually the most important case. But we also want to do this stronger with positive numbers up here from the from this big set. But we first do this one. And the idea is that given such a sequence, we can transfer the last term up to 1 over K12 by the definition of good, then transfer the resulting last term. Now we have a smaller last term. The resulting last term to 1 over 12, shifting what we already have, shifting all the positive stuff by 1 over K12, and continue this way until we get to 1 over K12 through n over K12. And we arrive at the same place for all y and z. We could start with the same y and z, with different y and z, the same x parameters, and then push y up to 1 over K12 through n over K12, and also push z up to the same thing. So therefore, we have equivalence. So that's why that holds. Then we have the stronger one. These are going to be star equivalent also. And this time we have a given y that may have positive part at the end. We first shift the positive terms so that they start with 1 over K12. Just shift them over so that they start with 1 over K12, then transfer the 1 over K12 to any R of I greater than the R's that we've used. And then continue in this way. So that takes care of those gaps, you see. By have two steps, push them down to 1, and then get rid of the 1. You push them down to 1 over K12, and then get rid of the 1 over K12, make them negative by using goodness, and then do it again. But you might start with something big positive number like 5 over K12, push them down to 1 over K12 and do it again, and keep doing that. So that actually gives us this. Now we can return to the language we really care about, because these other finite languages are auxiliary, and where we have quantifiers rather than the quantifier-free ones. And then we use the representation theorem for, see, the representation theorem for this throws us into this language for which we can apply our knowledge of what we did for this language. Okay. We use this language to help us get stuff for this language. All right. So first, this is the representation theorem. Now we already have this. This is our representation theorem for that we have from section 4.3, except that here we have positive numbers, 1 over K12 through 2a plus 2 over K12 instead. Actually, I should say this better because this Rn goes to here. So this should be 1. And we keep the Rn, sorry. So that's what we have. We keep the Rn and we have all these positive numbers. That's what we get from 433, but we can pull them down into the negatives because of what we just proved, all this stuff we just proved about sliding all these indiscernibles around, okay? So this is clear. And then this one, we're in this language again, and we want to prove SAT if and only if SAT, where this is the indiscernible stuff, where we're using these negative things instead of the positive ones, right? So all we do is we transfer back into the positive ones like we did up here. In other words, the first one is the Rn is kept over here. No, Rn is part of the assignments here. Let's see. Yeah. Okay, so first we apply theorem 433 to both SATs, and then we have the positive. We use some positive numbers. Then we can pull them down this way. Right. Yeah, The Q, yes, the Q in theorem 44433 in the representation theorem from section 3. Remember, it's a less than Q. So these less than Q's are used in here. And so we wind up with again applying the indiscernibility theorem we did with 4410. Yeah. Okay. In other words, we're combining the new indiscernibility with the old representation for this language. Yeah. All right. So that's where section 4 started. I mean, sorry, that's where section 4 ended, and that's where we started section 5 last time. So I think that this is pretty much what I wanted to say. All right, I'm done.